Okay, let me start. Okay, can everybody see my screen? Okay, great. Great. So my name is Zachary Nevin. I'm the CTO at thegraduate.com.hk. So let me just tell you a bit about what we do. We are an education company, right? So essentially what we want to do is we want to make every student valuable in tomorrow's world, right? And I'll tell you about how that fits in with our machine learning vision, right? So our vision currently is to essentially match students and tutors, okay? And the way that, and we could use that using humans, and we currently are, but we believe that machine learning can automate that process and make it just as good, if not better. Now, for the future, we could also do very interesting things with machine learning in terms of matching people to companies. But I'll talk about what we're doing currently with machine learning, what we plan to do currently with machine learning, which is to match tutors and students based on preferences and who will click with what tutor, right? So the problem is, how do you match out of 1,000? If I were to have, say, one of my employees do a match between tutor and student, they'd probably look at price or location or some kind of fixed variable. But what I'm interested in, and as a company what we're interested in, is knowing how to match based on variables that we wouldn't really think would be important, right? Patterns that we wouldn't really see out of potentially thousands of variables. And that's really something that humans aren't very good at, right? So while humans are very good at critical thinking and creativity, machine learning in its current form is very good at pattern recognition and understanding data, huge sets of data that humans simply can't filter through. So let me actually just go down the actual machine learning route, given that, or first about our technology. So on our platform, we're using a completely service-oriented stack. You may know it as microservices. So essentially, we have this orchestration tool called Kubernetes, which manages the lifecycle of a particular service. And we have decentralized our entire architecture. And that has actually been very good for us because it allows us to very quickly iterate and add new features in any language that we want. That's going to be really, really important for when we add new machine learning features, say, written in Python or C++. In fact, it's been so successful that we've done the same thing on the front end, right? If you go to our website, what you're seeing is actually a combination of 4 different front ends written in different stacks, different technologies. And the back end, while it looks like one back end, actually is a combination of about 10. But now onto the machine learning. So the formal definition of machine learning is that you have a program that gets better at a task T with, as it goes to experience E with some performance measure P, right? So that's the formal definition. And there's 3 different forms of it. So the supervised learning, so that's where you actively provide training data and use that to have your program get better at it. So a really good example of that would be our own matching algorithm, right? Where we would say have this data on students and tutors and a probability or a binary condition of whether they match or didn't match, right? And then we take that data and we run it through this algorithm saying, okay, right, this student and this tutor produced a value of 0, no match. And this student and this tutor produced a value of 1, which is a match. Then you train thousands, tens of thousands of those data points, and eventually what happens is your algorithm converges on a function that tells you whether this student and this tutor will produce a 0 or 1, right? That is, specifically that's called logistic regression. But there's other forms of supervised learning. There's unsupervised learning, and that's where you don't actually need to provide a training set. So that sounds a bit counterintuitive, except that you may have things like clustering algorithms. So k-means would be an example of an unsupervised machine learning algorithm. So would a self-organizing map, which is essentially a neural network that learns to cluster data in a lower dimension. So would and for supervised algorithms, you also have autoencoders, right? Which I'll get to in a bit. They're very, very interesting. And the other thing, which is one of my favorites, is reinforcement learning. So that's where you have this condition that that your algorithm strives towards, and that dictates the behavior of the system. So a very, very good example, which I'll touch on a lot, is an evolutionary algorithm. So in an evolutionary algorithm, what you might do is have this population go towards its end goal. So you would write this program in which you would spawn random members of a population, and then each of them would have some sort of fitness associated with them. And you call, say, a certain number of the bottom ones, and you keep going, and you have this algorithm that merges them together such that you kind of keep the correct traits. And then as you go through generations, you get agents that do what you want, right? So evolution algorithms are, in my opinion, incredibly amazing machine learning algorithms, just in terms of the things that you can do with them and what other people have done with them, and just in terms of the fact that they mimic biology very well. So let's talk a bit more about some other definitions in terms of ML. So one thing I want to clear up is the difference between ML and AI, at least in my opinion of it, right? So we have machine learning, and that's computational statistics, right? So you're training your computer to recognize patterns. So but there's no real intelligence associated with it, right? So a really good example would be the logistic regression that I touched upon earlier. So in the matching algorithm that I described, it wouldn't actually be truly intelligent. It would really be doing statistics, but automating a lot of that for me, right? Logistic regression is a statistical algorithm that you may encounter outside of machine learning. And one thing that you may find in machine learning courses is linear regression, and with gradient descent. And the thing with linear regression is that it's really just a fancy term for fitting to a line, something that you do all the time, right? Even polynomial regression, which is where you may have multiple variables associated with that. All those things involve taking this data and essentially fitting a function to it, right? Now, without regression, you do have these other very interesting machine learning models for doing similar things. One of those is a neural network, and there's several different types, right? So it's hard for me to articulate with just a screen, but in a neural network, what you're essentially doing is you're doing a series of nonlinear transformations, right? So if you've ever seen a neural network, you see these inputs, and then you see these hidden layers, and then you see some outputs. Right, so you can think of this as each layer in your neural network is itself a nonlinear transformation. So you do some nonlinear transformation for the data to a higher dimension, and then maybe some lower dimension, and so on, and keep going until you get an output. And the reason that works is if you think of it is that you can think of it topologically. So if I have a donut that's linked that is linked with another donut, I can't. A 3D torus, actually. If I have two linked 3D toruses, then I won't be able to separate them in 3D, right? Because they, if you think about it in terms of, topologically, you can't separate two linked toruses. But if you actually project that into 4 dimensions, you can separate them. So that's actually one way that neural networks work, if you think about it. Where if I have this data where there's this overlap in the dimensions given the data, I can use say a neural network to project it to a higher dimension and figure out how to separate it that way, and then project that into lower dimensions, say to give a binary classifier. But that's still computational statistics. So another example of a neural network would be a convolutional neural network. And that one's a bit misunderstood in layman's terms, but essentially what it is a network in which you convolve your inputs. So that actually plays a huge role in image recognition. So if any of you have ever studied image processing, what you'll find is that you use convolutions a lot. And in convolutional neural networks, it's essentially learning those algorithms, but better as well. So what you're doing in a convolutional neural network when you're doing image recognition is you are actually discovering through convolving these inputs and learning how these these different pixels can convolve and having different parameters for that. You develop a lower dimensional representation for your image, essentially, that you that basically encodes the information of your image, the information contained in your image that you want, in dimension that is understandable by, say, your NLP system. So a very good example of what I'm talking about is that you can actually take a convolutional neural network and you can take an NLP system, right? And you can actually map the outputs to the same space. So what that means is that you have, say, images of horses appear in the same positions as words that relate to horses. And that's actually how image tagging systems are powered, right? So you have these two different systems mapping their data to the same space, and then from that you can essentially read off like an image and the word that is associated with it, and maybe the translations for the words that are associated with it. So it's this, and that kind of falls under the this talk about neural networks that I'm going through now. It really touches upon something called deep learning, which has exploded over the last 3 years. But none of that really means AI. Now, AI and ML really mean the same thing to a lot of people, but to me it doesn't, right? So to me, AI means general artificial intelligence, right? Because I think of intelligence and learning as two different things, right? I can have a machine that learns something, learns patterns, but is not necessarily acting intelligently. Not intelligently in the way you and I would, right? So now, in my opinion, I don't think we're even close to general AI. And the reason I say that is because this explosion in AI, in ML that we've been seeing recently has been related to pattern recognition and deep learning, but still doesn't represent any true creativity or agency on part of the computer. It doesn't really represent, any sort of critical thinking skills. I think we're still a long way off from that, though it's an active area of research. And the last thing is NLP. So that's natural language processing. It's a subset of ML. It has really exploded in recent years as well due to deep learning. In fact, one thing I'll say is that with deep learning and this technique, which really only came about a few years ago, we have done more with it in the past few years than we have in the last 25 years combined of ML research. So to say that ML right now is a hot topic would be an understatement, because over the past several years, due to companies like Facebook and Google with their huge research arms in this area, we have seen we can do much more with it than we could before. So just to go through a case study, if any of you want to visit this link, this is basically JavaScript implementations of various evolutionary algorithms. Let me just visit it now. So, what this is doing is it's essentially going through different populations and trying to converge on a set of robots that will walk, right? And this actually has not this implementation in particular, but this algorithm, this evolutionary algorithm, has very huge implications for robotics, right? And teaching evolutionary algorithms can be used to teach robots how to be more autonomous, how to walk properly. You can imagine that try to teach a robot to walk by encoding rules is not possible. Trying to encode physics engine rules into them, given their different shapes and environments and terrains, it just isn't possible. But an evolutionary algorithm and learning how to actually walk, which to us is very easy, is something I think can be solved by evolutionary algorithms. The problem is of course processing power, because the processing power needed for a robot to use this kind of algorithm to learn how to walk is quite big. So let me just go back to this slide. Okay. Now, Sentient is a company based in San Francisco. They are a machine learning. They're an they're a machine learning company that has the goal to scale AI infinitely. So one thing they did was they produced a 1 million node system all over the world, and they deployed trillions of genetic algorithm agents to do trading. So these agents would spawn, they would join the population, they'd compete, and they'd die. That's how it was described. And there's so many other things they're doing with evolutionary algorithms. I think it's one of their favorite ones. They're doing a lot of medical applications with it. So one thing that they've done, and this is another example of why why machine learning is such a hot topic right now, is that they've used machine learning to detect sepsis 30 minutes early, which is life-saving and revolutionary. The third case study is Google. And I don't know how many of you know, but they recently came out with an algorithm to play Go. This is a deep learning algorithm. And the problem with Go compared to chess is that the board is much bigger and the number of possible moves that you have is, several orders of magnitude greater than the number of atoms in the universe. So using some kind of brute force method to play Go simply wouldn't have worked. But they did come out, and the thing that makes Go unique is that it's purely a strategy game, right? So the reason that humans are good at it is because we have the ability to strategize and understand the game. So the challenge is to put that into a computer. Now that's not to say that this computer could think. I don't believe it could. And that's not to say that we're any closer to general AI, because I don't think we are. That being said, even though we aren't closer to general AI, I still think that the AI that we have has a lot of value, right? I think currently we are at the brink of an AI revolution. I think it's only going to increase from here. I think there's going to be a lot of crossroads of technologies. I think that if we ever get quantum computing sorted out, that would accelerate the process even further, perhaps even give us general AI. It would at least speed up a lot of the algorithms that we have, because quantum computers are very good at matrix multiplication, which is something that a lot of these AI algorithms rely on. And the thing I want to say about the AI revolution is that, and I'm sure a lot of you have read, is that it will make a lot of jobs obsolete. But at the same time may create a huge number of jobs. What I will say is that a world in 20 years will likely be unrecognizable. And if you think that's far-fetched, think of how you understand our world today and if you would have understood it 20 years ago. Think of how different our world is now compared to 20 years ago. And think of that process accelerating, right? And one thing, because of that, I think this is a great time to get involved in AI. However, one thing I will say is actually make a note about general AI. Current AI can only really respond to stimuli. As I said, it can only really do pattern recognition. It can only respond to stimuli. And having something that can do critical thinking and general intelligence is very difficult. We can certainly simulate some parts of the brain, at least for a second, but that requires massive computational power. It's because of that, I don't want to get political here, but what I would be afraid of more in the next few years is not machines that are too smart. It's dumb machines being given too much power, right? It's machines that, say, are given the ability to kill. It's not that they have the ability. It's not that we have drones that they have the ability to kill. It's that these drones are not intelligent enough to have an agency like that. And that's what I'd be more afraid of. But smart AI is not something I'd be afraid of even in the next 20 years. I may be wrong, but it's what I think. So, right, challenges of the job. Now, I'm not formally an AI researcher. I'm the CTO, but with ML in particular, you have the ability. Being at the forefront of it right now, you are going to be working on potentially world-shaping technologies, right? the job is always very interesting. There's always a huge there's always a huge amount of data these days that are being fed into AI algorithms. So much experimentation being done. There's so much being done in machine learning, right? That jobs for people who do machine learning are in high demand everywhere in Silicon Valley, in Texas, and Boston. All these. What's happening is that I predict over the next 10 years that there will be a proliferation of AI startups and AI tools, much in the same way that there's been a proliferation of web development tools and jobs over the last 10 years. Right? I imagine the same thing is going to happen for AI today. In fact, we can already see what's happening with open source tools like Tensorflow. If you've ever heard of it, it's a tool developed by Google. It's a C++ library for doing deep learning. In fact, they use it internally in their own systems. So that brings me to trends, right? So the trend right now is in deep learning, right? So what deep learning means, if I wasn't quite clear on it before, is that you have these algorithms that don't really need to be taught historically, the way that you would do machine learning is that you would do endless feature engineering. So what feature engineering is you look at your data and you try and make sense of it yourself and say, okay, well, these features are likely to work and these features I shouldn't really care about. And then you plug that into your machine learning algorithm, you take a look at it, and then you evaluate it. You go back to your drawing board, you play with your features a bit, you put it back in, and that process takes weeks. So what deep learning is the ability to just, and that was applied to NLP, to image recognition. Before the top NLP systems in the world, before deep learning, were generally mostly hand coded, but now they aren't. So deep learning is scrapping all that. And it works in. It doesn't work in every context, but essentially what you do with deep learning is that you don't need to do endless feature engineering. Right? So you can take a bunch of text, you can take images and so on, and you can plug it into these machine learning algorithms, and it discovers the patterns for itself. And that has become tremendously useful in things like image tagging, right? Which is what I described before, which is this combination of NLP and convolutional networks. Because NLP, there's some really cool stuff being done in NLP with relation to recursive autoencoders, optical recognition, which I suppose is the same as image tagging, game playing Go. And as I mentioned earlier, we've accomplished more in 3 years with this in the last 25 years with that deep learning. To say that deep learning has been a success is an understatement. In general AI, though, it hasn't gotten quite as much attention. I think that's really because researchers see it as a bit of a dead end for the time being. It might be a computational power issue. It might be the fact that our computer architecture won't support it. It may be the fact that trying to simulate a general intelligence or a consciousness, and this is what some people believe, is similar to trying to simulate a chemical reaction. A chemical reaction in real life happens very quickly, mostly, but trying to simulate that on a computer takes days. So some people believe that consciousness and the way our brains work is something that is a physical property, much in the same way that a chemical reaction is, and that it's not really possible to simulate it. Only time will tell. One thing I actually want to draw upon is an autoencoder, because I do think that's really cool. So I'm sorry for actually skipping that over. But an autoencoder is a really nice nice subset of neural networks. So what you're essentially doing is you are encoding data. I don't know if you've heard of video encoders or audio encoders, right? So what they essentially do is they take some data and they compress it to a smaller format, but preserving all the information. And the way these work is on a principle that information and data aren't the same. I don't know if any of you have gone into information theory at all, but the idea of an autoencoder is that information and data are not the same, and that you can have a smaller amount of data represent the same quantity of information. So what you essentially do is you have this input layer that represents your vector that you want to encode, and you pipe it through to a hidden layer that has a smaller dimension than your input layer, right? Your hidden layer has a smaller dimension than your input layer. And then what you want to do is you want to pipe that to an output layer. Yes? Hello? Should I? Okay, and then you want.
Yeah, you may go on, sir. No problem.
Okay. And then you pipe that hidden that reduced representation to an output layer, but you train your output layer to reproduce your input. And the idea is that if I could take this x-dimensional vector and compress it or condense it to a lower dimensional vector and then reproduce my original vector, then that hidden layer that with the smaller dimension will represent the same information in my original vector. So, and what that also does is it eliminates features that you don't really need. So autoencoders are a feature deep learning that allows you to kind of strip out features and modify your features without doing the feature engineer. There's other types that like recursive autoencoders, and those are used in NLP. So in NLP, you'd have a recursive autoencoder that that essentially takes a sentence and understands its semantics. So what I mean by that is you have a word that has a semantic meaning associated with it, but a sentence itself can also have a semantic meaning associated with it. So what I mean by that is you can have two sentences that are different that have similar semantic meanings. They have similar meanings, right? So what you want to do is you want to have your NLP understand that. And the way you do that is with a recursive autoencoder, right? So the idea is that if you have two sentences that have similar semantics, then the words will also have similar semantics, right? But the sentences may have different lengths. So you want to recursively plug this into a recursive autoencoder, and the whole idea is that at each stage, so it's essentially autoencoders chain together, and at each stage you want to reproduce the inputs that fed into it, right? So at the first stage, I plug in two words, and I produce a condensed representation with the same vector length as each of the words. Each of the words are actually encoded as a fixed length vector. Then I would take that output and the next word and encode it. And then I take that output and the next word and encode it, and I keep going until I get to the end of the sentence. But what you actually do is you do that, and you do that with different orderings of the words. That's called a greedy recursive autoencoder. So, and then you take the best fit. So then that would encode your sentence into its semantic meaning, and then you can actually map that sentence to the same vector space as your words, which represents the semantics. And so what you can do is you can have sentences that kind of that mean the same thing, kind of map together. It's used in translations. It's new technology. I was reading a paper on it, I think about a month ago. Right. So I kind of digress a bit about autoencoders, and challenges and perks of the job. Okay, so of course you get to work on very interesting problems. This field is fascinating. It's one of those fields where you never stop learning. It's constantly evolving now, and there's a growing number of resources related to learning machine learning. There's Coursera courses coming up, there's Udacity courses. In fact, on our own platform, we have an excellent ML tutor who actually advised me, and his name is Ali. If you're ever interested, I'll do this. Now, for the skill set required to get this job, obviously you need very good programming skills. These skills usually require you generally need very good algorithmic skills in terms of graph algorithms and dynamic programming and all that. You need to be very good at statistics and understanding data and how to evaluate. You need to, of course, be trained in machine learning, and that's what I would say is a good idea of the kind of skill set you would need. It's definitely not an easy field, but it is very rewarding. So I'm going to leave that with a problem statement. So I actually came up with this today. So this actually touches upon an evolutionary algorithm. So I don't know if any of you have ever heard of the bin packing problem, but essentially you have a set of bins, right? A number of bins, and they all have different sizes, right? And then you have a bunch of fixed volume containers. You can have as many containers as you want, but you want to pack your bins into the minimum number of fixed volume containers, right? And this is a one-dimensional bin packing problem. You can actually have different types of bins and so on that you also need to pack into your containers. And that would actually come up in something like Google Cloud, where what they do is they have these resources like memory and CPU, and they have these clusters, and they want to kind of take these pods and kind of distribute them around the cluster with different replicas. And they need to do that where they kind of pack the stuff efficiently into bins by these different metrics. But I digress. So this is the bin packing problem, and it turns out you can actually solve it with an evolutionary algorithm, right? So you can keep. So I would fix the set that you have. So you have the set of X bins. You choose a set of X bins, and your evolutionary algorithm would kind of go through different bin packings of this, and with the goal of minimizing the number of containers that you have. So the fitness would really just be the number of containers that you have, right? If I have, I have this individual that has this bin configuration. When I have this individual that packs the bins in this way, I get this number of containers. So my fitness is, say, lower or higher. And then you can keep iterating that, and have these different individuals which each represent different bin packings, minimize the number of containers that you have. And the challenge in this is to get your data representation correct, right? So you need to figure out a way to represent your data in such a way that you can evolve it, right? And that you can merge these things together through, say, through a genetic process, and then come with new iterations and call old ones, and that works. Another problem statement I could have if you don't want to do an evolutionary algorithm is to write an autoencoder. I just made it up right now, so I don't really know what you write it in. But essentially, this is the one. And that concludes my talk.
Okay, do we have any questions coming in from any of the colleges? Vizag, Nagpur, Delhi? I think we have a question coming in from WeBind College of Engineering.
Okay, perfect.
Yeah, you can go ahead and ask the question to the sir. WeBind College of Engineering, can you hear me?
Yes. Okay. Well, there's several things you can do. So one thing that we're doing, now the challenge with recommender systems is that you may have a huge amount of data they want to filter through, right? Can we turn the, sorry. Yeah, so you may have a lot of data to filter through, and a lot of that data isn't really relevant. So what you could do is you could first take your data that you want to recommend, say in our case maybe tuners, in other cases maybe products, you cluster them, right? So you could use self-organizing map, you could use and then what you do is, say you would map to a particular cluster and then return everything from there. That's one way to do it. That's the way Google News works. So what Google News does is they feed through the internet, they crawl through the internet, and they look at all the news stories, they categorize them. And then when they categorize them, when you look at a news story, you're looking at other news stories in that category. So that's one way to do it. I feel like that's a fairly easy way to do it. And that's a bit more scalable. Another way to do it is to produce what's called this is kind of the old way, is to do it's called a co-occurrence matrix. So you essentially get your people and your products, and you have ones or zeros for what they bought, or maybe some rating. And then the idea is that similar people will buy similar things, right? So, so then what you do is you have to produce a matrix of people who are similar, and then use that to generate recommendations. It's actually like a formula that you use, just a single matrix calculation. The only problem I have with those, old recommendation systems is that there's really this cold start problem. With any recommendation system, right? Like you go to Netflix and, they don't know anything about you, so they have to show you these movies that, that they may not like, right? And that's not normally an issue, with Netflix and YouTube. If you watch a bad movie, that isn't really a problem. But in a case like mine, where, you have these student contracts that can last for months, then getting the right match the first time and getting around the cold start problem is a bit of a challenge. Any other questions? So, let me elaborate on the recommender system. So once you've kind of mapped to a cluster, you can actually use logistic regression. So if I have this person and this product, and it's 1 or 0, bought or didn't buy, or I have a number representing my rating. That's an interesting one. Actually, it turns out we can, and there's many companies doing that. And what they do is they would analyze traffic, for example, and understand what patterns are typically used by bots and scrapers, and block those, right? And I think so what they do. So there's companies that will protect you from bots by using machine learning. Now, we may get more sophisticated in the future with protecting cybercrimes, and there's a lot of research into this area, but I'd say yes, it is possible. At least for some of them. Yes, that's called a convolutional network, right? So you actually use a combination of NLP and a convolutional network. So what you do is you take an NLP system, and what it does is it maps words to a vector space, right? So you can imagine this space, and just imagine 2D, and you have words that are kind of sprinkled around the space. Then you have a convolutional network that takes images.
Hey, hello.
Hello. Hello. Then you have a convolutional network that takes images and maps it to the space. And then what you do is you essentially put your image through this. You figure out where it goes in this vector space, and then you read off the word that's associated with it. And yes, general AI. General AI would be an unresolved issue in machine learning. I would say that's the biggest unresolved issue. The fact that machine learning currently is only very good with, for which question? Image tagging? Okay, right. So for image tagging, what you do is you have a network, what other people call a neural network, right? In fact, what you would use a special type of neural network called a recursive neural network. So so instead of having kind of this fixed length of inputs, you can put it in as many words as you want, and you map your words to a vector space. Now what you do is you have a convolutional neural network, and you map that to the same vector space, right? So and the way that works is that you first produce a representation of images, of words, right? By producing this, this representation of words produced by a recursive neural network, and then that's fixed, right? And then you map your images on top of that. So for example, I would have this image and it has this representation after my convolutional network. And then I train, okay, this is a horse. And then I do back propagation, right? And I train, okay, well, this is something else. And then, my convolutional neural network would learn to produce representations of images that would map correctly to this vector space. So then what you get is this shared representation space of images and words, such that images and words that mean the same thing are close together. So you get horses, cats, types of cats, and then what you do is you put your image through, and then you read off the word or the words, and then you tag it. Now, in terms of actually tagging images for sentences, that's way more complicated, and that really goes into to really new technology, year-old technology related to recursive autoencoders and recursive networks. And I don't really know how that works in particular, but it is something that you can read academic papers on. Okay, and for recommendation systems, yes. So for recommendation systems, my general strategy would be to first cluster the data, because then your data will grow logarithmically, right? If more people come on for products, say you have this person who looks at, who's looking at hair dryers, right? You don't want to feed through every single product and see if you can recommend that to them. You kind of want to fit everything within the same category, right? So when doing a recommendation system, how do you recommend that you cluster your data first so that your data grows logarithmically? And then you can do something like logistic regression. That works pretty well. There's also some matrix methods that you can use. I'm not too familiar with those. But yeah, there's a lot of stuff. My preferred method is to use logistic regression and clustering. For unresolved issues in AI, I would say general intelligence is the biggest one. We don't yet have any model for how consciousness works, for the fact that we have agency. We don't have any model for having computers make decisions. I mean real decisions. I don't mean decisions based on patterns. I mean decisions based on creativity and understanding. For example, we can't yet have a machine that passes an 8th grade science test, and that's an 8th grade science test with all the images removed and all the, and put into this very standard format. I think one of the issues is that it's, the AIs that we're building are limited in how they represent data. And what I mean by that is, when we have our brains, they take sound and images and everything else, and they process them, and they go through these different processing stages into this kind of reduced representation that is then understandable by these other systems in the brain. When you take something that needs to play video games, it's not like you can just kind of sit in front of a computer and have it play video games. That video game needs to be put into a format that it can understand, right? If we didn't have any of our senses, that the same would be true. But I'm not sure when we'll solve the question of general intelligence, and I'm hoping I'll see it in my lifetime. I'm sure we will. Right. Yeah. So I would start with, you mean like where do you want to learn it?
So if you could just repeat the question for the audience who don't have the screen.
Right. If we would like to include machine learning in research, from where would we generally start? Do we start from statistics? So do you mean like if you want to learn machine learning, or if you want to use it in a project? I would actually look at something called Tensorflow. Right? It's by Google. Let me send you a link. Right. So Google just came out with this, and let me just go back. So here, I'll share my screen again. So this is TensorFlow, and here's where I would start. Right, so you define and this looks a bit confusing at first, but essentially what you do is you define, because what your machine learning is a data flow graph, right? So for a really good example is, I first want to take my data and plug it through a neural network. So that would be take my data and putting it through a neural network. And then I want to take the data that's output from the neural network and put it through softmax. So that would be here, for example. And there's loads of stuff you can do with this, right? So you can do recursive neural networks, you can do recursive autoencoders and autoencoders, you can do neural networks, you can do all the other standard machine learning algorithms. This is, I would say, the best place to start with machine learning, by far. And Google uses it internally. In fact, they made it. Stop sharing my screen.
Do we have any questions from Yashwantrao College of Engineering? Hello? Yogesh, sir. Professor Yogesh, do we have any questions from Yashwantrao College of Engineering? Any questions from Vizag Institute of Technology? Professor Safi, do we have any questions from your side?
No questions, sir.
No questions. Absent.
Absent, huh? Bye bye.
So I think that's it. Thank you, sir, for such an insightful session on machine learning from the technical perspective. I'm sure you have inspired and showed a way forward to a lot of students present here who may go ahead and take this up as a career option. Thank you, Mr. Nevin, once again for your time, sir.
It was my pleasure. Thank you.